All right, what we're going to be doing now is laying the foundation for adding vectors that don't fall into one of those nice categories. So we're looking on page 32 of your unit handout, I believe, where we're going to be adding vectors using components. I want to be very clear. What we're learning today, we're not going to do to answer questions like the ones from yesterday. Okay? And that will come out in the lesson as we go through this. We're going to be starting off by defining components of vectors and finding components, and then we're going to be adding vectors using those components. And we're going to be using this method of adding vectors because anything we've learned prior to today won't work. Okay? So, quick review. There's 3 different situations that we've encountered when you're adding vectors. And again, I'm dealing here with displacements because it's easy for us to think about. But the same rules could be applied to adding forces, which are vectors, or velocities, which are vectors, and we will get to that tomorrow and the next day, or electric fields, which are vectors, which we deal with in Physics 30. But the 3 basic situations are these. If 2 vectors are in the same direction, the sum of the vectors is found by adding the magnitudes and attaching a direction to the result. This is so simple, right? So if I said to you, what is 35 kilometers west plus 55 kilometers west, you can add these 2 together. Please do not get ahead of me in your notes, just follow along up here. You can add these 2 together and get what I believe is 90 kilometers west. Okay, so this is 90 kilometers, and the direction is west. And again, very, very basic. That's the first case. And I would say that it requires almost 0 thought and certainly no work. There's nothing you have to write down on paper to explain this. The second case is if 2 vectors are in opposite directions, the sum, and sum means add. You add the vectors by subtracting the magnitudes. You're not subtracting the vectors, you're subtracting the magnitudes of the vectors. And you attach a direction to your answer that's the same as the direction of the larger of the 2. So if I change this a little bit and have 35 kilometers west and 55 kilometers east, well, you have more kilometers east, so you subtract them and you get 20 kilometers east. Third case, and this is what we led up to on Friday, if the 2 vectors are perpendicular to each other, then you use the Pythagorean theorem, and you also use a little bit of trigonometry to find the angle. So if I had 35 kilometers west and 55 kilometers north, again, you draw these tip to tail, and you can do this to complete your note package. You do need to have vectors being indicated with a direction. What does that mean? You need arrowheads. You don't just need lines, you need arrowheads. You know, you can feel free to use a ruler if you want. You don't need one when you do this, but your diagram should be decent, is maybe the word. This should be completed nicely. So we find the hypotenuse and we find the angle. And again, very basic stuff. I'm actually showing some work here on the board as opposed to what I did earlier, which was just on my calculator. You know, that hypotenuse squared equals 55 squared plus 35 squared. So you work that out, you get 65 kilometers. Probably don't need to remind you, don't forget to take the square root, but don't forget to take the square root. And for some reason, oh, there we go. Tangent is opposite over adjacent. I guess I'm pointing out to you, and I don't know if I did this on Friday, that this is on your formula sheet. There's a section on the physics formula sheet called trigonometry and geometry. And there's all kinds of other stuff. There's your formula for slope, areas of rectangles and triangles and circles. But in the end, SOHCAHTOA is on there. There are also some other trigonometry formulas, but you haven't learned about them yet unless you've taken Math 20. So you apply that, you take the inverse tangent of that, and you get 58 degrees and it's north of west. Okay? The reason why these angles were highlighted is I wanted to point out to you, I think it's obvious, but that 55 is opposite the angle, the 35 is adjacent to it, and that's why you're going to use tangent. All right. Well, it turns out if it doesn't fall into those categories, you can't use any of those strategies. You have to use what are called vector components. So what are vector components? Vector components are going to be broken into horizontal and vertical categories. And what vector components are the equivalent horizontal and vertical part of a vector. So this says the horizontal or x component of any other vector is a single vector that describes how far east or west a single vector points. So it may be that the single vector is pointing kind of towards the north and east, but some of it is towards the east and some of it is towards the north. The vertical vector, oh, and there's a typo in your notes. The word of should be in there, I think. Otherwise, when you read what I have in your notes, it doesn't, like, what's he saying? The language is tortured. It says the horizontal component, any vector. No, the horizontal component of any vector. Just make a note of that. The vertical component, and again, I believe there is a error there in your printout. The vertical component of any vector is another single vector that describes how far north and south the original vector points.
We're also missing need in the first one on our page.
Pardon me?
Well, we also are missing the word need on the first sentence at the top. Not up there, like in the book.
Okay. You're saying this word is not in your handout?
Yeah.
Okay, thank you. And I'll fix that in my handout. Not sure why that happens, because typically I'll just copy the text from my original and put it here, but anyway. You get the idea, though. A horizontal component of a vector is a east vector or a west vector telling us how much east or west the original vector is. And a vertical component is a single vector telling us how much north or how much south the original vector is. So, draw a vector diagram for a displacement of 400 meters, 30 degrees north of east. This is pretty simple. What I've drawn is not a vector right now. I'm just drawing an arrow, and I used a dotted line to indicate that that's east. You don't need that arrow. You could just put a dotted line. But I put the arrow there because that tells me I'm going to start drawing my vector from this point right here. And I have to imagine facing east and then rotating my position so that I will be walking 30 degrees north of that, which means in that direction. When I asked you to draw two perpendicular vectors, I always say draw the horizontal first, and then your angle is north of or south of. This is north of east. And in the end, anytime you follow this north of or south of, coupled with drawing the horizontal first, your angle is always measured from the horizontal. Your angle in your triangle that we're going to construct will be against the base of the triangle, nowhere else. So that's the vector. It is 400 meters long. And we're asked to find, so we've drawn the vector, there it is. It's a single vector. We're not adding anything. We're on page 32. 33. We're on page 33 right now. Find the horizontal and vertical components. Well, if you started in that position and walked 400 meters, 30 degrees north of east, will you be east from where you started? I don't mean directly east. Will you be more east in your final position than you were to begin with? In other words, will you be at a different longitude on the map? Of course you will, right? If you walk 400 meters, 30 degrees north of east, Will you have traveled north in the process? Yes. You will have traveled east and north. And would you agree that if you walk 400 meters 30 degrees north of east, I could get to the same position by walking east, stopping, and then walking north? That's what the components are. The components are going to be two vectors. So this is the displacement, right? That whole thing is the displacement. But part of that displacement is to the east and part is to the north. These are our two components. So your next step when we find those components is to draw those two arrows. Now, did the person walk along those gray lines? No. But walking along the gray lines is the same result as walking along the vector 400 meters 30 degrees north of east. And what that means, look, just this is tricky for some people, I get it. But do you agree that if I add those two gray vectors, I get the hypotenuse? If I gave you those two gray vectors and said add them, you would have drawn them tip to tail to get the red vector. Here we're working backwards. What we want to do is we want to find those two components. There's an x component and there's a y component. Quite frankly, once again, very basic Math 10. It's SOHCAHTOA. You're familiar with that slang, SOHCAHTOA?
Yeah.
Why are you laughing? Somebody pronounce it in Klingon?
Yes.
Yeah, okay. SOHCAHTOA, right? Something like that? That's the Klingon pronunciation of SOHCAHTOA. So how do we do this? Well, we look at that angle that we know, and here's another useful tip. If you draw your horizontal first and your vertical second, in other words, if your angles are always north of or south of, then you will always be using cosine to find x and sine to find y. Always. The minute you move that angle to a different location in the triangle, you, in the words of my dad, upset the apple cart. Which, I don't know if you've ever heard that before. It means you change things. Things get messy. And the reason for that is when you take a look at that 30-degree angle and where x is adjacent to it. And if the angle is against the horizontal, x will always be adjacent to the angle. So when we take a look at our formula sheet, we've got cosine is adjacent over hypotenuse, sine is opposite over hypotenuse. I would suspect you probably didn't get to this course by having to look at that all the time, but if you forget, it's there. You probably remember it. So what do? Well, cosine of 30 degrees is x over 400. It's adjacent over the hypotenuse. And sine of 30 degrees is y over 400. Now, I want you to keep in mind something. I didn't put 400 meters. I'm just talking about the dimensions of this triangle. And I would like everybody to find, it doesn't really matter. We'll go to 2 decimal places, I guess. I don't care about significant figures here. I would like you to calculate both the horizontal and vertical components if you haven't done so already. And I get, well, I guess I'm just going to the nearest whole number. But rounded to the nearest whole number, I get 346 meters. And I will get exactly 200 meters for y. Those of you in Math 20 right now, in my class anyway, you will learn y. I know that y will be exactly 200 after tomorrow's lesson. But it's 200. So what are the components? This is not good enough for an answer. That's not the answer. We need to say that the horizontal component of that vector, and look at the notation here. It's not just some haphazard writing out of an answer. It's displacement, which is a vector. The vector symbol is there. In the horizontal dimension, or the horizontal direction, is 346 meters east. And we can write that the vertical component of that displacement is 200 meters north. Pretty straightforward? Did somebody in here just say, oh my God, or was that from the hallway? Okay. Couldn't tell with my precision hearing. Those are your two answers. Explain the relationship between the original vector and the two components of the original vector. This is so important. When you add the two components together, you're going to get the original vector. Like, literally, what I mean is dx plus dy equals d. That's what we're saying. The x and y components added together give the displacement. This is a true statement, and people look at this and go, I think you're kind of pulling my leg there, Mr. Way. Because if I add 346 and 200, I don't get 400. This is not saying add the magnitudes, it's saying add the vectors. How do I add a vector in the horizontal and a vector in the vertical? I draw them tip to tail and find the hypotenuse. And the hypotenuse is where we started. The difference is we were finding the hypotenuse vector, the total vector last time, by adding easts and norths. Here, or wests and norths or whatever, here we're working backwards. So that's the relationship. All right. Add these vectors. I've given us all the tools we can, that we need to add these vectors. So first of all, let's break this down. Are these two, well, you know what we should do first? Let's write these angles in a more sensible way. North of, south of, all that stuff. So remember, when you see angles like that, that's called RCS. And RCS is measured with 0 degrees here, and the angle is measured counterclockwise from 0. So you need to figure out what 135 degrees is in a more sensible way, and you need to figure out what 90 degrees is in a more sensible way. I'll be honest with you, you will never see RCS on an exam. I've included it here because I want to show some of you who are going to excel in math a very interesting thing about RCS. Okay. Well, 90 degrees is north. Right? When you rotate 90 degrees from 0 up here, 0 is essentially what I'm saying is east. 90 degrees will be pointing north. If I were to take a vector and rotate it 90 degrees, in other words, it's north. If I rotate this vector 135, just using my calculator or my brain, I'm already at 90. If I want to get to 135, I have to go 45 more. And that means that this angle of 135 will be 45 degrees in between those two axes. I could write 45 degrees east of north, but I would much rather write 45 degrees north of east. So this one is 100 meters, 45 degrees north of east. Okay. So that's just a preliminary thing. We've taken those two vectors and we have written them in a way that we're used to working with. Now, question. Are these two vectors in the same direction? Are the two vectors we're trying to add in the same direction? No. So you can't just add the numbers together. Are these two vectors in opposite directions? No. So you can't just subtract the numbers. Are these two vectors perpendicular to each other? No. So you can't draw them tip to tail and use a right triangle. Well, what you do then instead is what we're going to do today. We write x and y components for each of these vectors. So that's what we're going to do. I'm going to get rid of this other stuff. It's just in the way. Quite frankly, I don't think many of you needed to write it down. So what I want to do is find a horizontal component of this vector and a vertical component of this vector. And I want to find a horizontal component of this vector and a vertical component of this vector. So what we are doing is we are going to break this down, this problem down, and we're going to change it from having two vectors to add together to having four vectors to add together. So let's start with the first vector, 100 meters, 45 degrees north of, I have made a mistake, haven't I? And I mentioned this on Friday that I will often make this mistake because you're facing the paper one way and I've got to face you. What's the mistake here, Noah?
It's west.
West, yeah. I need north of west. There you go. So to find the components of this 100-meter vector that's 45 degrees north of west, we're going to do the exact same thing we did here. All this work we did here, we're going to do for the 100 meters, 45 degrees north of west. We draw in a dotted line that's along the east-west direction. I draw in a vector that I can label as 100 meters. You have to determine a horizontal and vertical component of that vector. And somehow I wonder, yep, I had this all set up. Look at this. We've got that. You have to determine the x and y components of those vectors. Okay. Pretty straightforward. With this vector diagram, those are our two components in gray. And I don't know, how many of you understand that since it's at 45 degrees, your x and your y components will have the same magnitudes? Right? The sine of 45 degrees and the cosine of 45 degrees are the same because these two vectors are equal in magnitude, because it's an isosceles triangle, 45, 45, 90. So I would like everybody to calculate that. I'm showing all of my work here. I don't know how much work you would like to show. But, and again, you would learn in Math 20 how I'm able to find these numbers. I think they're both going to be 70.7. Of course, 70.7. So you get 70.7 and 70.7. Now what about the 120 meters north? Like there's no triangle. Jacob?
The x would be 0 and the y would be 1.
Exactly. The x is going to be 0. There is no east or west here, and the y will be 120. By the way, you should put directions on those vectors, right? 70.7 meters west, 70.7 meters north. So when we do the x and y for the 120 meters north, we can put 0 meters for x. And by the way, we don't put east or west for that. 0 meters is 0. It's just 0. And we can put 120 meters for north. Are you with me on what we've done so far? What we have actually done, everybody, is we've gone from adding 2 vectors together to adding 4. We've made the problem bigger because we don't need this anymore. This is the same as those two. So we're done with this. We don't need this anymore because that's the same as those two. So rather than adding these 2 vectors that I've crossed out, if we add these 4 vectors, we'll get the sum of the 2. Because 2 of these highlighted vectors give us one of the 2, and the other 2 give us the other of the 2. So if we add the 4, we get the sum of the 2. It's like I've taken 2 objects. I've taken 2 pieces of paper, this piece of paper and this piece of paper, and I want you to find the total mass of this paper. And I've said, you know what we're going to do? We're going to do this. Why? Because I'm trying to make a point. And this, and instead of adding the 2 original masses, we're going to add these 4 masses. You're going to get the sum of the 2 masses, right? Okay. And you can add these vectors in any order you want. Can you add 2 of these together in your head? Absolutely. The 2 x's you can add together. And the two y's you can add together. So now what we can do is we can say the total x is 70 meters west. And guess what? We're done with. And we can add the y's together as well and get, is it 190.7? Is that correct? Okay. Guess what? We are now done with all of those highlighted vectors, because we can use that instead for the x and that instead for the y. So we went from from 2 vectors to 4 vectors. Then we went back to 2 vectors, but the difference is these 2 vectors that we have here are perpendicular to each other. And you can add those vectors together. Grade 9s. I know, you were in grade 9 at one time too. We can add these two together. You can add 70 meters west and 190 meters north very easily. Right? This is what we do now. So it appears as though when we take those 2 original vectors and we break it into components, we've made the problem more complicated. We've got more vectors to deal with. But we do so that we can whittle all of those components down to a single horizontal and a single vertical. And finding these 2 things is child's play. Right? Pythagorean theorem, tangent. I'm going to give you a minute to make sure that you can calculate those numbers. I've chosen just to round things to the nearest whole number for both the magnitude and the angle. I don't think it really matters. Because we're in a learning mode right now, right? We just want to know how this is done. That other stuff, that's parsley on the fish, how to round it and all that. That's other stuff that's not that important right now. So are you able to get 203 meters? I just want to confirm that what I've got up here is correct as well. And it's 70 degrees north of east. North of west, there I go again. See, I've got my east and west backwards. It's north of west for sure. Good? Okay. And again, that's the one I very often mix up my east and west because of how I stand. I don't mix up north and south because I'm not on my head. But my left is your right and my right is your left. So, all right. Let's try one more. And then that'll be it. Okay. So, very quickly, everybody. Are these 2 vectors in the same direction? No. So you can't.
Yes.
They are? No, they are not. 20 degrees north of east is not the same direction as 60 degrees north of east. The fact that they both have east and they both have north doesn't mean they're in the same direction. If you walk 20 degrees north of east and I walk 60 degrees north of east, we are walking in different directions. We're going to end up in different places. Okay? They're not both north, they're not both west, they're not both south, they're not both 40 degrees north of east. They're at different directions. So you can't simply add the numbers together. Are these 2 vectors in opposite directions? No. So you can't subtract them. Are these 2 vectors perpendicular vectors that we can construct a right angle triangle from? No. So that means we have to break them into components. You need to take each of these vectors and draw them one at a time. So there's the 7 kilometers, 20 degrees north of east. And here's the 4 kilometers, 60 degrees north of east. and you need to find x and y components. And what I would like seeing on your diagram, and I know that some of you are going to not want to do this, but I'm asking you to, please, is I want to see those horizontal and vertical vectors drawn in. Right? I would like to see this. I'm not putting that burden on you to be difficult or to make more work for you. You are going to learn something from continually doing that that will be helpful as the physics gets more complicated in this course and in Physics 30. And again, every vector diagram you draw, every length of a vector needs an arrow on one end of it. You can't just draw a triangle. So how are we going to do all of this? I'm not a big fan of this click-through thing. I don't know why I decided to do that this time. I'm going to leave these up here and give you a few minutes to calculate them. I haven't really shown any work here, but listen carefully. The angles are between the horizontal and the vector, and that means we can get used to the fact that a vector length multiplied by the cosine of the angle will give you x, and a vector length multiplied by the sine of the angle will give you y. May I take a quick peek at your formula sheet? They used to actually have those formulas on your formula sheet telling you that x and cosine are connected and y and sine are connected. So I can keep track of people's progress here. Can you put your hand up and down once you've had all four? Okay. And I'm assuming that they're correct. So for the 7 kilometers, 20 degrees north of east, you would go 7 cosine 20 to get the east, and 7 sine 20 to get the north. Now, why did we do this? Because those two brown vectors that you're looking at are not vectors that if we draw tip to tail, you can find the total. Because they will not form a right angle triangle. But we can add these two easts together and get a single east. And we can add, as well as the two easts together to get a single east, we can add the two verticals together to get a single vertical, which will be north. Are you with me on this? So we're done with that because we can use these two. And we're done with that because we can use these two. Now you should be trying to carry as many decimals as possible, but again, we're in a learning, teaching mode right now. Right? That's the dialogue we're in. So I'm not too worried about that. If you have difficult time managing these numbers on your calculator, I can certainly help you with that later. So now we can add the total x. Which are these two vectors. Are these two vectors in the same direction? Okay, then just add the numbers together. And you get a single x. Are these two numbers for the total y, are these two in the same direction? Are these two vectors, rather, in the same direction? Yes. So we can add them together quite simply. If one of these was north and the other was south, then we could also add them quite easily. You would just add them by subtracting the magnitudes. So now we discovered that the total east is 8.58 and the total north is 5.86. We're done with those. And we're done with those. And now, so you've gone from 2 vectors to 4 vectors, back to 2 vectors, but the 2 vectors we started off with were not perpendicular, so we had an issue. The 2 vectors we ended up with were perpendicular, or are perpendicular. And adding these together, these 2 highlighted vectors, is, we're in taking candy away from the baby territory. Very simple. Find the hypotenuse, find the angle. I'll give you a minute to finish this problem. Bless you.